Okay, thank you for the introduction, Dominic. If I'd known that this would be your first experimental talk, I'm not sure if I would have been brave enough to accept the invitation, but thank you anyway for the opportunity to speak to you all. Our work is motivated by the push to build programmable many-body systems. And the payoff of doing this is, twofold. It's the quantum simulation of interesting Hamiltonians, including those of interest to those of you in the condensed matter theory community. And then also, not entirely non-overlapping is quantum information processing. And the point is that if we can realize a sufficiently large, fully controlled quantum many-body system, then we can do things that are just not feasible to do on classical machines. And what do I mean by programmable? Well, without fully defining it, it's to give you a taste, it would be something that's a fully tunable system Hamiltonian or fully tunable experimental platform. And the things that we should be able to tune are things like, if it's a spin model, then the transverse and longitudinal fields, tune the interactions, tune or control exactly how we address the system, and so on and so forth. And the challenge, of course, is to do this programmability on systems of increasing size while maintaining full quantum coherence within the system. Let me put this in the context of what has already been done in some comparable platforms. So for instance, people have been working with neutral atoms trapped in optical lattices, and there one of the goals is the quantum simulation of the Fermi-Hubbard model, with system sizes currently of something like several hundred atoms. The trapped ion community have achieved some of the highest qubit fidelities in our field, and on their platforms they can start running some quantum algorithms with a few tens of qubits, or there's quantum simulation of many-body Hamiltonians with several hundred ion crystals. And then on the right here, I show two examples of achieving a claim of so-called quantum supremacy by doing various sampling problems. And in the superconducting qubit community, there was this very high-profile claim from Google of sampling random circuits and achieving quantum supremacy with about 53 qubits. And then just last week, published in Science, people in China have claimed the quantum advantage doing the boson sampling problem with about 50 photonic states. So as you can see, the state of the art of the field is somewhere between tens and hundreds of particles for your quantum many-body system size. What does that mean for our platform of Rydberg atom arrays, and what are its advantages compared to the other platforms that are out there? Well, because we work with neutral atoms, there's a path to making really defect-free arrays that are highly scalable. So with increasing system size, we have a path to getting larger and larger atom numbers. These experiments, this is an experimental detail, they have much faster cycle time than some of the comparable, for instance, optical lattice experiments. And that's important for the kinds of experiments we can run, the kinds of algorithms, the kind of stability we need, and the kinds of data acquisition rates we get. Our systems, I hope you'll see from the rest of my presentation, is remarkably tunable in terms of geometry, interactions, and so on and so forth. And we have the capability of doing local state readout and then also local control of the system via single site resolved readout and addressing and these kinds of things. And then finally, just comparing to the other platforms, we are getting to be very competitive in the kind of fidelity and quantum coherence that we can achieve. And whereas previously the best Rydberg systems have been about 50 atoms fully controlled, now with this work, we show that we can extend this to many hundreds. And so this combination of all these 6 features really means that Rydberg atom arrays are starting to become one of the leading platforms for doing programmable quantum many-body systems. With that, I can tell you the outline of what I plan to present about our specific work in the rest of this seminar. So I will first tell you about how we actually make these defect-free arrays of Rydberg atoms. And then one of the first things we do to benchmark how well we can realize a coherent quantum many-body system is we prepare very high-fidelity antiferromagnetic Néel-ordered states. But going beyond that, in our system, we actually have a full and very rich phase diagram of many interesting phases, and we map out this full phase diagram experimentally as just a demonstration of the power of our system, both in terms of tunability of system parameters and the single site readout that we can, that's just built into our platform. as a demonstration of our ability to quantitatively probe quantum phases and quantum phase transitions, we actually identify and characterize a quantum phase transition in the 2+1D Ising universality class. And then finally, there's a very novel and intriguing phase with superposition of Rydberg excitations, on the array that's stabilized by quantum fluctuations. And I'll tell you a little bit about how we probe the nature of this novel phase. Since I'm talking to a condensed matter theory community, let me start introducing our experimental platform by telling you about the Rydberg Hamiltonian that we realized on our experiment. So our platform consists of individual neutral atoms. So in our case, rubidium-87, trapped in an individual optical tweezer, so trapped by the optical dipole forces. And if there were just this one atom, then we use a 2-photon coupling between a ground state and a highly excited Rydberg state via some off-resonantly via some intermediate state, and this realizes just a 2-level system with Rabi coupling omega and 2-photon detuning delta, where this n sub I is just the population in the excited state, either 0 or 1. That's all fine for individual non-interacting atoms, but now if we have other atoms nearby, then the fact that this upper state is a Rydberg state actually becomes important, and we start having this second part of the Hamiltonian, that's the interparticle interactions. And the atoms interact via a van der Waals 1 over r⁶ interaction, where r is the separation between the atoms. The reason for this interaction is because whereas, if I represent the wave function of the ground state as this circle, then the wave function of a highly excited Rydberg state has a massive spatial extent in comparison. And that means that this Rydberg state is highly polarizable. And so these two adjacent atoms can interact via very strong induced dipole-dipole interactions. And that's the origin of this C6 over r⁶ interaction. What this interaction does is, so if we have a pair of atoms, both in the ground state, well, if they're separated far enough, then we can couple them resonantly to having either through this intermediate state with one excitation, and we can drive both up to the Rydberg state simultaneously. So that's just two atoms individually driven by our as a 2-level system. But now, if the atoms are close enough spaced such that the Rydberg van der Waals interaction is larger than the coupling omega, then the interaction energy shifts the driving off resonance. And so we can only ever excite one atom in each pair, the Rydberg state, at a time, and we're forbidden from having simultaneous Rydberg pair excitations. This effect is what's known as the Rydberg blockade. And you can parameterize it by something called the blockade radius, which just measures the interaction strength C6 relative to the driving. And the point is that only one Rydberg excitation is ever allowed within one blockade radius, RB. You can already begin to see that under the blockade effect, if you are only allowed to drive this transition, then the state that you realize is actually an entangled state of an excitation on either of the two atoms. So it's with this Rydberg interaction, Rydberg blockade mechanism, that we realize interesting many-body entangled states of matter using our Rydberg Hamiltonian. So let me tell you about what we've done previously with our experimental platform. So the very initial experiments in our lab were done with 1D array of defect-free atoms. And the approach was to load neutral atoms probabilistically into the optical tweezer sites. And then you do imaging readout and see which tweezers don't have atoms in them, and turn those tweezers off, and then via a radio frequency sweep, move all the tweezers next to one another, all the remaining tweezers next to one another, until you have this defect-free one-dimensional chain. And this amount of spatial control is essential because, as you'll recall, the van der Waals interaction is 1 over r⁶. So you really need to be able to deterministically locate the atoms in order to have, to be able to prepare a specific kind of interaction in your system. Okay, so with these 1D arrays of atoms, we next.
Sorry, can I ask a quick question about the slide you just had?
Yes.
So what you're showing here, is this possible as like an intermediate state? Basically, so what I mean is, would
the top row possible as an intermediate state?
Sorry?
Are you saying is the top row possible? Which one?
No, I mean, like, measuring the holes and then making a defect-free system. Is it something you do in practice before continuing with the experiment, or it's more subtle to do it in practice as some kind of?
In the experiment, we load and then we do a projective imaging readout to see the random loading, and then we rearrange, and then we do a second projective readout to make sure that we do have a defect-free array, and then we do all the Rydberg Hamiltonian physics, and then we do a third readout, which is the readout that we tell the theorists what the results are.
Perfect, thank you.
Okay, great, thank you. Feel free to interrupt if you have questions as I go, and then I'll pause at a few points too to solicit questions. Okay, so using this Rydberg interaction in the 1D system, we can realize Rydberg excitations spaced apart with Z-in symmetry, just depending on the Rydberg blockade, and then we can probe the quantum phase transitions into these ordered phases and look at the quantum Kibble-Zurich mechanism. Since the Rydberg blockade is a mechanism to give us entangled states, we can demonstrate really high fidelity preparation of entangled pair states of atoms, or we've even pushed and demonstrated a record 20 atom maximally entangled GHZ state in our system. And then finally, we can combine all these ingredients and implement high fidelity qubit gates with 2 or 3 qubits. And so the question then at this point is, can we scale this platform up to 2D? And the motivation is, well, we can control a larger quantum system in 2D. We can explore some more interesting many-body physics, and just in 2D, you have higher connectivity for realizing qubit gates in our system. How do we get to 2D? Well, instead of a fan of one-dimensional tweezers, we actually imprint onto a laser beam an arbitrary phase profile using a spatial light modulator that's programmed on a computer. And then when that phase profile is projected into the center of our vacuum chamber through a high numerical aperture objective, the result is a 2D periodic array of optical tweezers. And then using this method, we can generate something like, definitely over 500, about between 600 and 1,000 individual optical tweezers. And this is just one of many realizations of this 2D array approach. There's a number of other experiments. This is not necessarily an exhaustive list, but there are many people who are using similar techniques to do experiments very much related to ours. What does this look like in our experiment? On the left, I show an example of just an image of the actual optical tweezer, so not atoms yet. And then on the right, this is an animation of actually loading atoms probabilistically into those tweezers. And this is actually a realistic experimental cycle time of several hertz. Each side is loaded with about 50 to 60% loading probability. And so the question is, can we take this random loading and pick a target region, for instance, and fill that target region perfectly with atoms? In the experiment, how do we do this in practice is we just try to move the atoms up to the very tops of the columns until they fill each column. And so what you might do is you might pick out, well, first we superimpose another set of optical tweezers that move in both X and Y, controlled by an arbitrary waveform generator. And that realizes some moving tweezers that you can pick up and drag and drop off individual atoms. And so for instance, we can target these 2 atoms that are not in place and move them up until they fill up the target region, and then we can repeat with some more pairs of atoms, and we just repeat this process iteratively, sweeping our optical tweezer beams and picking up and dropping off atoms until we eventually fill the target region perfectly. So let me show you what the experimental results might look like. So in this animation, our initial loading is on the left, and then after we do the initial loading, we do this atom rearrangement, and a typical result is shown on the right. So it's not perfect. There are some defects in this array, but if we just keep running this experiment, every once in a while, as we do this readout, we can post-select on a single instance of having a perfect array of up to 300 atoms, let's say. The numbers are something like we can realize over 99% filling of this array, which means we have a decent probability of post-selecting on perfect rearrangement for system sizes of up to a few hundred. our system is programmable. The location of our tweezers are just determined by the phase profile, which comes from a computer generated pattern. And so we can do more than just realize square arrays. We can certainly do square arrays of very large sizes, but we can also do hexagonal. We can make triangular arrays, kagome. These are all things of interest to the condensed matter community, of course. But beyond that, we can really have arbitrary patterns for where the atoms are. So for instance, we can have this arbitrarily chosen target pattern where this might realize some kind of natural graph geometry in terms of nodes and connectivity. And then we can say load atoms into exactly those sites. And the result is indeed, we can actually put atoms exactly where we want them. Well, given all of this control over our atom loading, what else do we do when we have some fun in the lab? We make atom videos, as some of you may have seen already. So each frame in this video corresponds to one projective readout of the rearranged atoms, and we stitch them together to make fun, publicity videos like this. I'll pause here with this video and ask if there are any questions so far about the experimental platform. Okay, great. The video was too mesmerizing, so let me move on. Okay, that was how we make our arrays in 1D and 2D. Let me begin to tell you about some of the ordered state and the physics that we're exploring now with our Rydberg Hamiltonian. So I've already told you about the Rydberg Hamiltonian. In 2D, this is a rendering of our experiment. The atoms in 2D are trapped in the middle here, and then we send in laser beams from either side to realize a 2-photon coupling on the system. And with this Hamiltonian, if the detuning is negative, then the ground state is all atoms in G, in the ground state in the atomic ground state. When delta, the detuning, is positive, then the many-body ground state is basically as many atoms as possible excited to the Rydberg state, but subject to the Rydberg blockade constraint. And I'm sweeping under the rug that delta has to be less than 0, but relative to the transverse field omega. But this gets you the idea. And delta here is in effect a chemical potential on our Rydberg excitations in condensed matter language. So then what happens on square arrays? Well, let's think about what the Rydberg blockade does. And as a reminder, Rydberg blockade means that within a blockade radius, only a single atom can be excited to the Rydberg state. We can tune this blockade extent not by tuning the blockade radius, which is determined by the excited Rydberg state principal quantum number we work with, but we can actually tune the array spacing because we can place the atoms exactly where we want. And that tunes the blockade extent RB over A. So how many array sites over which Rydberg blockade occurs. The simplest thing to consider is just nearest neighbor blockade. RB over A is about 1. And this is the smallest value that gives us an ordered phase. What happens in this case? Well, if we have a Rydberg excitation here, then that blockades its nearest neighbors. And so the next possible Rydberg excitations are on the next nearest neighbor diagonals. And if we just keep on going from there, the ordered state that's possible on this system is this antiferromagnetically Néel-ordered checkerboard state. How do we actually prepare this checkerboard state? Well, we start with all atoms in state G. And then we quasi-adiabatically vary the detuning from negative to positive so that the system follows the ground state quasi-adiabatically into this Néel-ordered checkerboard state. Let me show you what that looks like in our experiment. So this is a defect-free array, 15 by 15 or 225 atoms. And when we do this adiabatic sweep, this is an example of a perfect checkerboard ordering. The red circles here, those denote atoms excited to the Rydberg state. They're detected as lost because we only image ground state atoms by fluorescence. We don't image atoms in the Rydberg state arm. We can also do the same with another bipartite lattice like hexagonal, and we get, again, an example of perfect checkerboard ordering. These images are, of course, very post-selected, but I can tell you something about the fidelity of state preparation. So for instance, if we look at the histogram of microstate occurrence, because we have individual readout, we see that, okay, well, there's there are a lot of states that only show up once, right? That's the peak in the histogram here. But way out on the right end, there are two states that occur a very large number of times relative to the others. And if we look at the microstates, those are actually, in fact, the two complementary antiferromagnetic orderings. We can also characterize the fidelity of our preparation by looking at the probability of realizing the perfect checkerboard state as a function of system size. And that probability follows a trend line of 0.97 to the power n quite well. So from this one line, you can already pick out with what probability we can post-select on one of these images. A complementary characterization or demonstration of the fidelity of our system preparation is to think about how large is the correlation length in our system, how large is the antiferromagnetic ordering correlation length. And to do that, we use this connected two-particle correlator. And for a perfect checkerboard ordering, this alternates between 0.25 and minus 0.25. So what does that look like when we do it on all of the projective measurements of our experiment, post-selected not on final perfect checkerboard, which of course would give the perfect alternating ordering, but post-selected on defect-free initial rearrangement of a 15 by 15 or 12 by 12 or whatever size array of ground state atoms. And if we do that for a 12 by 12 system, this is what we get. So you see, the color bar goes from minus 0.5 to plus 0.25, and there is the alternating correlations pretty much across our entire array. We can characterize this with a correlation length by fitting exponential decays to the correlations along the horizontal and vertical cuts, and our correlation length is over 11 sites across our 12 by 12 checkerboard array. So this is correlations and quantum correlations across an entire system of over 100 quantum particles. And just to make the observation, this is an order of magnitude higher than the correlation lengths that have been observed previously, which has been just about 1 to 2 sites.
Can I ask a question here?
Yes.
So you're presenting like a large correlation length as I guess it's a good thing in a sense that shows you have a lot of coherence, but if you want a more localized state, like, is it a tunable parameter based on making delta larger or smaller, I guess?
Is the correlation length a tunable parameter?
Yeah, I guess if delta becomes large enough, you will approximate something closer to a product state. Is that wrong?
I mean, if we don't go, I think we can certainly tune the correlation length, or we can realize different correlation lengths by changing the adiabaticity of our sweep, right? And when it's less adiabatic, then there are just more domains, and so the correlation lengths are smaller.
Yes.
And then if the detuning goes high enough, then the chemical potential starts to overcome the Rydberg blockade, and you go back to a product state of just all atoms in the Rydberg excited state.
Sure, I don't mean that high. Well, I don't want to change the preparation because that's basically, then you're not preparing the ground state as well. What I guess I mean is have different ground states for different parameters, but they would all be in the same Néel phase, right? You could have a psi as a function of a tuning parameter. Are you saying this large correlation length you see here, is this due to the preparation, or the ground state actually has such a large correlation length?
So if we had a perfect checkerboard state, the correlation length would be infinite. So this is a measure of how close to perfect preparation we have.
Oh, this is not factoring out the order. I see. But if you would subtract the ordering pattern, right? Like the how to say? But you say, do you not bias one ordering pattern over the other? Are you saying both ordering patterns are equally likely?
So that's a good point. So with this measure, if we just had only a single checkerboard always, this would actually give 0, right? Because the NK and L on different sides would be completely independent.
But you have quantum fluctuations, no? That's my
pardon me?
What I'm getting. You would have fluctuations above an order. Are you saying
so? What I'm trying to say is that if we have an odd by odd system, then we pin a particular antiferromagnetic ordering because it's more favorable to have Rydberg excitations along the edges. But the point of doing this on an even by even system is actually, in fact, that we see both antiferromagnetic orderings with near equal probability with a projective readout. And so the ground state should be a superposition of these two.
But even on
so maybe I comment.
yeah.
Can I comment, Ruben? he's in the ordered region, and so the correlation length in the ground state is strictly infinite, even though the moment might go down. I mean, I think what the quantum fluctuation will show up in the moment, the magnitude of G2KL, right, not the correlation length.
Yes, correct. Initially, I was not aware it was it was not subtracted. Like
this is the it's the no,
yeah.
This is the connected correlation. Sorry, I take my comment back.
Yeah, that's why I was a bit confused. But I think it's connected, but then it's fine because it's even by even. But if you do odd by odd, then the connected is still interesting because it will tell you about the quantum fluctuations relative to this.
Yeah, so we will get something non-zero for odd by odd because even though the edges are pinned, there is still fluctuations in the bulk.
Okay.
But in any case, my understanding, you're going to talk about the quantum phase transition, so I'm sure you're going to show data with different correlation lengths.
Yes, but definitely so. Okay, let me continue, but thank you for the really great questions so far.
Actually, maybe I can ask a question also along the same lines. If you just go back, you had the values for different parameters in this particular setup.
Yes.
I think so the delta T is the preparation time, is it?
Correct. It's the time of the adiabatic sweep.
And if you go much slower than that, does it improve your state preparation, or you're pretty much in the ground state already with this kind of sweep time?
So this is the optimum that we found in our experiment. This begins to be limited by the finite decoherence on our platform. So we can't go too much further. So right now,
I see.
There are a number of routes and ideas we have for improving or suppressing the decoherence rate, which will allow us to be more adiabatic. Yes.
I see. And what's the dominant source of decoherence? Is it the coherence of the lasers, or is it something else?
So there's some probability of off-resonance scattering from the excitation lasers. There's also the finite lifetime of the Rydberg state itself. There's some stranger kind of experimental details like correlated cluster losses of Rydberg atoms that we see on our platform. So those combination of experimental things pretty well account for this 3% error of our checkerboard preparation.
But the phase coherence of the laser itself is much longer than these kind of times, is it?
Yes, it is.
Right. Thanks.
Our laser line widths are something like 50 kilohertz.
All right, thanks.
Thank you for that question. Okay, let me tell you about a couple of other order parameters that we can use to analyze the checkerboard ordering, because that will become important as I start talking about how we map out the whole phase diagram. So the checkerboard ordering has staggered magnetization, and so then this is a natural order parameter. It's this order parameter is +1 or -1 for the two opposite checkerboard orderings, and so then to get a measure of the fidelity of checkerboard preparation, we take just the mean of the absolute value across all projected measurements. Since the checkerboard is a spatially ordered state, we can also take a spatial Fourier transform. So given something like this, this is a binarized perfect checkerboard where purple is ground and yellow is Rydberg atoms. Then we take this Fourier transform, and the Fourier transform gives us a peak at k equals pi pi. And if you look at that peak, well, these weights here for k equals to pi pi just correspond exactly to staggered ordering. And so basically, the Fourier transform peak at pi pi is exactly equivalent to the staggered magnetization. The phase of the Fourier transform, it just distinguishes between which of the two antiferromagnetic orders you have. And so then, again, we just throw that away, take the absolute value, and average that over the projected measurements to form our order parameter for the to form a measure of the quality of checkerboard ordering in our system. Now I'm ready to tell you how we go beyond just the checkerboard phase and explore the entirety, or explore a much wider region of the phase diagram on our 2D Rydberg array. This phase diagram has been mapped out in considerable detail by Subir student Ryan. And the checkerboard state is down here. So checkerboard ordering starts right about when you start nearest neighbor blockade. And then if you go above square root 2. So if you, so this is checkerboard state. If you go beyond the diagonal neighbor blockade and go further, then you have this star ordering, and this is what it looks like. You might expect that if you go beyond diagonal next nearest neighbor, then the ordering should be every 2 sites. And that's true, except that the van der Waals interaction has a long range tail. And so it's actually energetically favorable to offset the excitations like this. So it's you're placing excitations slightly further away, but the excitation density is still the same. So that's the star phase. And it's called star, I guess, if you take one of these excitations at the center and connect it to all its neighbors, it makes a very nice star pattern. But now between the star and the checkerboard phase and this small sliver, just when you're within the region of some blockade of the diagonal next nearest neighbor, there is a strange phase called the striated phase. And in this phase, it's actually energetically favorable to weakly violate the diagonal blockade condition. And so the result is that these yellow sites are not quite 1, they're less than 1. And these green sites are slightly greater than 0 in terms of Rydberg excitation. And this kind of partial excitation ordered phase, the ordering depends essentially on the fact that you have a transverse field. And the full nature of this striated phase, I'll devote an entire final section of my presentation today to tell you about how we characterize it. What do we see on the experiment when we look at the phase diagram? We can definitely see examples of star ordering. If you look in the bulk, this is a post-selected image of very nice every 4 excitations in one direction, every 2 excitations in the other direction. Because of those spatial periodicities, if you do a Fourier transform, you expect peaks at these 2 locations, and then of course also at their symmetric partners because of the number of different orientations that are possible for the star. Likewise, if we probe the striated phase, we see, the backbone every 2 excitation, every 2 sites excites the Rydberg state, and then with the occasional blockade violating excitation in the middle here. And because the striated phase is this partial ground Rydberg, we only ever get a projective measurement of that in the real space readout images. This ordering has these Fourier transform peaks along with the symmetric partner. And so it's with this information of what the Fourier peaks are for these respective orderings, it's with this that we're going to start mapping out the phase diagram experimentally and try to see where the order parameter for each phase is the strongest and where the phase boundaries are. So let's talk about the order parameters. I'm going to define this F tilde just to take care of this symmetric partner business, just a symmetrized Fourier transform weight at both symmetric partners. So for the star phase, it shares a peak pi0 with striated, but it has a unique peak. So let's pick that to be the order parameter for the star phase. For the striated phase, it shares a peak with star. And so let's have the order parameter for striated be the difference. Let's subtract out the contribution of the order parameter for the star. This is nice because this difference for a perfect star ordering is exactly 0. And so we're really picking out the Fourier weight corresponding precisely to striated ordering. With the same motivation, we define the checkerboard order parameter to be a difference of the pi peak, and then subtracting the striated pi0 contribution, because striated has also some pi component as well from the blockade violating local checkerboard patterns. And so with these 3 order parameters, which are non-zero in the phase of interest and 0 in the kind of adjacent phases, we're now ready to experimentally use our single site readout, construct our Fourier transforms, and figure out within our tunable Rydberg Hamiltonian where the phases exist experimentally. In practice, with experiment, we just do a linear sweep at a constant Rabi coupling, and we just go with various endpoints. And at each endpoint, we do projective measurements and characterize the order parameter. We we tune the blockade extent, again, by varying the array spacing A, so we can map out everything in the vertical direction, the blockade extent, as a function of the effective chemical potential delta over omega. The results from the experiment look like this. I show a false color plot of where the order parameters for checkerboard, for striated, and for star are strongest. And you see that they occur at different regions of the phase diagram, RB over A and delta over omega. And then for comparison, the red points are numerics from Rhine using DMRG on a 9x9 array with open boundary conditions. So you can see for the checkerboard, this lines up beautifully. And then there is, it also gives a sense for what we're seeing for the striated and star orderings as well. The other thing we can do is we can compare with numerics, we can actually also generate these order parameters and see what they look like from numerics. And you see very nice agreement between what we see in the experiment and what we see through numerics. So I'll pause here, and before I go on to the last two topics of my talk, I'll pause and see if people have any questions about what I've told you so far about checkerboard fidelity, and then about mapping the full phase diagram.
Actually, can I go back to this question of timescales for preparation?
Yes.
So I think I'm a bit confused about is it looks like your Rabi frequency is, it's like megahertz, right? A few megahertz.
Yes.
Which is, I mean, the corresponding timescale is like microsecond, which is also your preparation.
No, it's a Rabi time is, a Rabi pi pulse is 100 nanoseconds.
Oh, I see. And how does that square with this, your omega being megahertz?
Well, a pi time is 250 nanoseconds, and so pi is about 100 something.
Mm-hmm. I see. So in the time that you prepare, you get a few Rabi oscillations. Is it? Is that how I should think of it? It's
yes.
Maybe, yeah, and that's sufficient for you to establish these nice ordered patterns.
That's right. I think this number maybe more concretely is 1 to 2 microseconds. So we're in the several to 10 Rabi oscillation.
I see. Thanks.
Okay, having mapped out the full phase diagram, let me tell you how we deploy the capabilities of our experiment to quantitatively probe a quantum phase transition on the system. In particular, we probe the quantum phase transition into the checkerboard ordering. This is predicted to be in the quantum 2+1D Ising universality class, which, because of the Lorentz invariance of the theory, has the dynamical critical exponent z equals to 1, and then the correlation length critical exponent nu, which is 0.63. And we'll try to characterize this value of nu experimentally to probe the nature of this quantum phase transition on our experimental platform. We do this again with a linear sweep into the phase at various endpoints. As an experimental detail that we can talk about more at length if anyone's interested, instead of doing what previously was a finite time gradual turnoff, we actually do a sharp cutoff at the end of our sweep and make our projector measurement. So if we do that, as a function of detuning, the growth of correlations across the quantum critical point looks something like this. Right. The color bar here shows that this is for a range of linear sweep rates spanning about an order of magnitude. And the insets just show some visual illustrations that the G2 correlation function does get bigger and bigger as we go further and further into the phase. Now, this quantum phase transition quantum phase transitions of a particular universality class in general have universal scaling of both the correlation length and time across the quantum critical region. And so we can actually, if we rescale the correlation length and the the tuning parameter distance from the quantum critical point by these equations, then we get universal rescaled correlation lengths and detunings. This rescaling is as a function of the sweep rate, S, and then relative to some arbitrary reference, and with exponents that are determined by nu and z, the critical exponents of the quantum phase transition. And so the point is that with the correct rescaling, all these curves should collapse onto a single universal curve. And so our measure of, we fix z to be 1 as a given, and we measure nu by just measuring what value gives us the best collapse of all of these correlation growth curves. Okay, if we define a metric for the distance between curves, the metric is we take a particular sweep rate, SI, and then for that sweep rate, we do a linear interpolation of all of the points, and then we compare the values at the linearly interpolated curve to the correlation lengths for every other rescaled growth of correlations for every other sweep rate. Okay, and then we just do this across all possible permutations to get this properly kind of symmetric evaluation of the distance between any pair of curves, basically. And when we compute this distance metric with our experimental results, we can plot it in terms of both the unknown quantum critical point, delta C, and the unknown critical exponent, nu. And the color bar here is some arbitrary scale for the collapse distance. What you can see from this is that if we take cuts across several presumed values of the quantum critical point, well, the collapse would be ideal at a number of different values of the critical exponent nu. So to know what the nu is experimentally, we really have to have an independent determination of the location of the quantum critical point. Because we're trying to verify if nu is consistent with 0.63, the prediction from 2 + 1D Ising, relative to the mean field prediction of 0.5, or the 1 + 1D Ising that was previously measured in our group of 1.0. How do we determine the quantum critical point independently? Well, we look for the quantum critical point as the peak of the susceptibility in our system. The mean excitation, the mean Rydberg excitation n bar, that's just an effect of magnetization in our system. And so if we take the slope of that with our tuning parameter, which is the detuning delta, then that is a good measure of our susceptibility, and we can take the peak of that as an independent measure experimentally of where our quantum critical point is. This equality here is just, this is approximately true if we remain in an eigenstate of the Hamiltonian, and so it's true as long as we it's an approximation that we stay in the ground state of our system. Okay, let's look at the experimental data when we try to do this. This is magnetization as a function of detuning across the quantum critical point. Okay, and so what we do is, instead of fitting this whole curve, we zoom in on a central region, and then we fit that central region. And what we do is we actually fit it to the lowest order polynomial that gives us a peak, which is a cubic polynomial. The derivative would be a quadratic, which would give us a peak. And so this helps us avoid systematics with how many a degree of this helps us avoid systematics of how large a degree of polynomial do we try to fit the whole data to. We just pick a narrow region, we fit a very simple polynomial, and then we extract where the peak of that susceptibility is. We keep an eye on the quality of the fit, so the chi-squared, the reduced chi-squared metric, to make sure that a cubic fit does indeed give a good fit, but it's not overfitting either. And so with this kind of a experimental analysis, we can extract the quantum critical point as something like this in units of delta over omega with a corresponding uncertainty. Now, going back to the collapse distance metric, if we make a cut here of where our independently determined quantum critical point is, you can already do some analysis by eye and say, okay, well, then the minimum of the collapse happens somewhere here, right? And which seems to be consistent now with nu predicted to be 0.63 for the 2 + 1D Ising universality class. Let's actually take a look at what that cut looks like. So again, we're trying to collapse this growth of correlation curves, and we're trying to see for what value of nu this best collapses all onto one single universal curve. And if we do that, we see that along this cut, collapse is ideal at nu is 0.62, and at that value, indeed, all of these sweep rates across the order of magnitude give correlation growth that collapses very nicely onto a single universal curve. And from this, we can quantify on our experiment this determination of the experimental nu, which is completely consistent with what's predicted through theory. And so to our knowledge, this constitutes the first observation of this canonical 2 plus 1D Ising quantum phase transition. I'll end my talk by telling you a little bit about how we probe this very last novel, strange phase called the striated phase that's stabilized by quantum fluctuations in the system. And so we have these two orderings, checkerboard and star, and these you can think about them as some kind of classical dense packing of excitations problem, right? And in contrast, this striated ordering is, because of our transverse field, it actually becomes energetically favorable to slightly break the diagonal blockade in order to get more total mean Rydberg excitation in the system. So then if we think about what this phase actually looks like microscopically, we can define some kind of unit cell here, and we call the sites with mostly Rydberg excitation as the 0, 0 sublattice. We define the diagonal neighbor site where there's just a small amount of blockade violation. We call those the 1, 1 sublattice, and then the other two, the 0, 1 and the 1, 0 sublattice, nothing is happening. They're fully blockaded by this by the 0, 0 sublattice. Okay, and so this constitutes a unit cell for the striated ordering. And so then we can say, well, let's just make the simplest wave function ansatz. On the 0, 0 sublattice, it's a superposition of G and R, mostly in R, but some small component in G, and so it's in the XZ plane. And likewise for the 1, 1 sublattice, again in the XZ plane, a coherent superposition represented on a block sphere, but mostly pointing in G. And then how do we actually probe whether the striated phase is of this nature? Well, we do quench experiments. We do quasi-adiabatic state preparation, and then we immediately afterwards jump to some quench time with a particular quench detuning that's variable, and also a quench phase that's variable. So this is looking at the striated phase through non-equilibrium physics. And this is an example of many-body interaction spectroscopy, because the 0, 0 sublattice sites, so these ones in red, they don't really have much around them in terms of Rydberg excitations. The other dominant excitations 2 sites over, the interaction energy falls off very quickly with 1 over r to the 6th. And so basically, we expect that their resonance is going to be pretty close to the single atom resonance, which is 0 detuning. But this 1, 1 sublattice, it now has 4 diagonal next nearest neighbors that mostly have Rydberg excitation nature. And so then these have an interaction shift of 4 times so this should be n next nearest neighbor, 4 times that interaction, which is about 20 megahertz. And so those sites should respond at a shifted frequency based on our model for how this ordering looks. And then the other two, the 0, 1, 1, 0 sublattices are fully blockaded, so no dynamics are expected to occur there. And then as another detail, if we, since this is a block sphere picture, it matters whether we're doing the quench along plus y, which corresponds to quench phase is pi over 2, because that is a rotation around plus y, which de-excites the 0, 0 sublattice. Or if we're quenching around the opposite phase, around minus y, then this corresponds to an excitation of the 1, 1 sublattice. Putting all those things together, if we do the de-excitation quench, we indeed see that the 0, 0 sublattice does get de-excited at close to the 0 detuning for the single atom resonance. So there's some small shifts because there is still some diagonal next nearest neighbor interactions. In contrast, if we do the excitation quench, then the 1,1 sublattice clearly shows a peak at the expected value of around 20 megahertz. And then, not surprisingly, the 0,1 or the 1,0 sublattices, nothing much is going on at all. Since this is since our wave function ansatz is a block sphere coherent superposition of G and R, there should be some coherence if we vary the quench phase continuously between +π/2 and -π/2. Right. And so if we do that at the de-excitation dip, we indeed see coherence as a function of the quench phase. And likewise, if we do it at the excitation peak of 20 megahertz. So then this represents our best effort at characterizing the nature of the striated phase, that it does seem like it is a coherent superposition of G and R throughout the array that's stabilized by the transverse field omega. With that, I've told you about everything that we've done on our Rydberg array with a square array geometry. Let me just conclude by giving you a sense of the future directions of our experiment. It would certainly be interesting to probe quantum phase transitions into some of these other phases in the phase diagram with harder to quantify order parameters and also harder to, it's not entirely clear what the universality class for some of these phase transitions are. So we can already use our tools of quantitatively probing phase transitions and deploy them elsewhere in the phase diagram. We've also been doing other non-equilibrium dynamic experiments where we, again, use quenches similar to what we did with the striated phase, but these quenches are now showing examples of non-thermalizing, non-ergodic quantum scar behavior, and then with suggestions of time crystalline phenomenon as well. We can map our Rydberg arrays with the atomic locations and their nearest neighbor interactions onto a graph theory problem with nodes and links. And then the Rydberg Hamiltonian naturally hosts the solution to the maximally independent set problem. And so how can we do through adiabatic preparation or through shortcuts to adiabaticity produce ground states that are solutions to the maximally independent set problem. That's an active effort as well in our lab. And then finally, there were two papers that were just posted on the archive from our collaborators, and these suggest that we can actually see signatures of quantum spin liquids on Rydberg arrays of the Kagome geometry. Beyond these active efforts, we also can imagine what a future ideal experiment might look like. And there are a number of ingredients that are within reach for Rydberg atom arrays that we're very excited about for expanding the programmability and the tunability and just the quantum many-body control of our platform. So for instance, being able to realize full single atom control, both sigma Z and sigma X operators, we've been able to demonstrate that previously in 1D, and we're a few steps away from being able to realize that in our 2D array as well. Other groups, for instance, the very productive efforts from Antoine Broese's group, they've been able to use resonant, not 1/r⁶, but 1/r³ interactions between pairs of Rydberg states coupled via microwave interactions, coupled via microwave drive, and they can realize different Hamiltonians than ours, for instance, the XY spin Hamiltonian and the SSH model. We're certainly interested in going to larger system sizes while still maintaining preparation fidelity on our platform, and also at the same time pushing the limits of fidelity and coherence to be truly competitive, or even to leapfrog some of the rival platforms for quantum information processing. Because of how we can move our atomic qubits around with our optical tweezers, there are some interesting ideas for actually spatially distributing entanglement within a quantum antibody system. And then finally, we have some adventurous ideas for potentially being able to do all of this, but in a complete three-dimensional geometry. With that, I'm going to leave you at this acknowledgement slide to say that all this work here was done with the benefit of an exceptional team of researchers, and in particular, the lead author on the work that we've done with 2D square arrays is our super graduate student, Sephora Abadi. And I'll leave this slide here, and that's the end of my presentation. I'll be happy to answer any final questions you have.